A box with a square base and open top must have a volume of 364,500 cubic centimeters. We wish to find the dimensions of the box that minimize the amount of material used. Answers must be correct, 3 decimals. Okay. So we have a box here, and it's telling us that a formula for the surface area of the box, that's the material on the outside, the surface area, in terms of only x, length of one side of the square, is there. Now, we found that in another problem, how we get that formula. So now we're finishing the problem. Find the value of x that will minimize the amount of material, the amount of surface area. So I want to minimize the amount of material, which is the surface area. So we got to take that formula, yes, which is x squared plus, oh yeah, and I'm going to rewrite this as 4 times that 364,500. I'm going to make it x to the minus 1, right? X on the bottom, x to the minus 1. Okay, and how am I going to minimize that? Right? Because that's what a company would want to do, right? They know how much they got to hold, minimum material. Take the derivative and set it equal to 0. You know how to minimize things. Minus that minus 1's going to come down there. Or the numbers will just sit in the front. X to the minus 2 because you subtract 1 from the power. Okay, and then what? Set it equal to 0. That's how we find maxes and mins. Right? We find where the derivative is 0 because that's where your peaks and your valleys are. Okay, so what we're going to do to solve this thing, we're going to bump this to the other side. So we get 2x equals positive 4 times 364 over 500. And I'm going to make that over x to the positive, right? Negative powers jump to the bottom, and positive, right? So now we're trying to solve for x. What should we do? Well, I'm going to multiply by x squared over 1, or just x squared on both sides. Cancels out here. And we have 4 times 364, 500. Over here, x squared times 2x cubed, right? Still solving for x. Divide by 2. Boom. So x cubed equals 2 goes into 4. 2 times 2 times 364, 500. Last step, raised to the 1/3 or cube root, same thing, 1/3 power, cube root, whatever. That'll get you x. Let's go to Desmos. 2, 364, 500. 2, 364, 500. 2, 364, 500. 2 times 3 is 500 to the power of 1/3, right? 90. Look at that. Beautiful. There it is. Nice, clean 90. That is the answer. So so who would care about this? Like, so companies that want to, they have a certain amount they got to haul. 364,500 cubic centimeters of volume is required to carry something. But you'd like to make a box. There's different shapes. You can make it tall and thin or flat. What size, what dimensions is going to make you able to hold that volume and use the least material? So if it's expensive material that you're making something out of, or if you just have millions of boxes, you're trying to minimize your cardboard use to save on every box. This is the dimensions. You should make this 90 and this 90, and we can find out what y is, but we're not going to bother. You can find the y. Um, and then you would know exactly how to make that box that will hold what you want and use the least material possible. And so that's how that works.